Today's discussion is going to talk about the Wolff-Kishner reduction. And in this reaction, we take a ketone or an aldehyde, and we treat it with a molecule called hydrazine, which looks like this. And with that hydrazine, you have it, you can create two kinds of conditions. You can create acidic conditions or basic conditions. We're first going to look at mildly acidic conditions. So if we put in some acetic acid, and let's see, and that's going to be, I'm giving you all the details here. Acetic acid, and that's going to be in some water and some glycerol, diethylene glycol, actually. Okay, that's going to be step 1. And then step 2, so that's our acidic conditions, and then step 2, you add sodium hydroxide, so basic, and then you add quite a bit of heat there. And what's going to happen is that you can take this ketone, or better yet, this carbonyl group on this ketone and reduce it and replace it with 2 hydrogens, like that. So you may encounter situations where you have a molecule that has a carbonyl group attached, that is a ketone or an aldehyde, and you want to get rid of it. Then you can, and by getting rid of it, you are replacing it with 2 hydrogens. Okay? But this Wolff-Kishner reduction does not work with carboxylic acids, amides, esters, or anhydrides. It's just specifically for ketones or aldehydes. Okay? And then the other conditions that you could use, I'll just show you that right now, where you could take just hydrazine, okay, under basic conditions, and then you have your water mixture with your diethylene glycol, and some heat. Now, do you see the difference between this one? You're going to get the same product, like so, but the conditions are slightly different. Up here, we're doing it in 2 steps, in acidic conditions, and then you add it to the base. But here, it's just 1 pot, and you get the same step, or the same product here. So what I want to do is, I want to show you the mechanism for this top one, because it's going to go through some reactions that we've seen before, and so it's going to help us remember things that we've seen and how we can use things that we've previously learned to figure out the mechanism for this reaction here. So the first step that we're going to do is we're going to take our ketone here, and we are going to treat it with step 1. And that first step, what that's going to do is it's going to convert your aldehyde or ketone into a hydrazone. And a hydrazone has a double bonded nitrogen attached to the nitrogen there, NH2 like that. So that's a hydrazone. And you see how that hydrazone right here, these nitrogen species, is coming from the hydrazine. Like that. So we have hydrazine that's used to convert the ketone or aldehyde into a hydrazone. So that is the first mechanism that I want to focus my attention on. And this, to go from here to here, it is analogous to amine formation. Remember that mechanism? How do you form amines in mildly acidic conditions. It's the same mechanism, more or less. But let's go through it and take a look at that. So we have here our hydrazine. Okay. And those nitrogens have lone pairs on them. And then we're going to have some of the hydrazines that are going to be protonated because we've added the acetic acid, mildly acidic conditions. So some of it's going to be protonated, some of it is not. And we are going to invoke the unprotonated version here to do that. Now when we do this, we're going to get this species here, negatively charged, and then we have our nitrogen, and 2, and we still have our 2 hydrogens on here, so that's going to be positively charged like so. Now, what is that step right there? Okay. That is our nucleophilic addition step. There's our nucleophilic addition step there. And now we can then do a proton transfer. Do a proton transfer there with this acidic version. So I'm going to expand that out so we can see the mechanism. So we have a hydrogen, hydrogen, and a hydrogen coming off like that. That's and so we're going to do a proton transfer like so to give us OH like so, and H2, that's still going to be positively charged right there. Okay? Now we need to do another proton transfer. Another proton transfer to get rid of one of those hydrogens there. Okay? So we can invoke a basic species here. So we could say, hey, let's use another hydrazine. We could use another hydrazine to come in here and do our proton transfer. Like so. And so I'm going to draw that molecule over here. So now we have this guy. We have our hydrogen there and a lone pair, like so. Okay. Now what's our goal? We want to make the hydrazone. So we need to get this guy to leave. Okay. And so we just generated some more acid over here. And so I'll put this piece right here was now converted into this, the acidic version. What are we going to do again? Another proton transfer. So we take the lone pairs on that oxygen, come grab that, and like that. So what have we done? We've converted the alcohol into a better leaving group. So that's going to be positively charged. And H2 like that. Now it's a good leaving group, so we would do a heterolysis step. So do a heterolysis step. And what does that look like? Well, the leaving group can leave like that, heterolysis step. And now what do we have? We have our nitrogen species. there. And then what is left? Water is left. But because water is left, that carbon now only has 3 bonds, so that's going to be positively charged. But we can anticipate here that we have resonance stabilization here because we have what? We have this lone pair right here that could resonate down to help stabilize that. So we have a resonance structure that looks like this. Now we have positively charged species there. Okay. Now we can invoke another proton transfer here. So we can come up here and say, hey, we need to do another proton transfer. And so do we have some base around? Yeah, we have some hydrazine right here that we could invoke. Say, hey, let's take some of that hydrazine and do another proton transfer. Like so. And then that's going to give us what? And there is our hydrazone. So this mechanism that I just showed you is very, very similar to imine formations. When you take a ketone or aldehyde and treat it with a primary amine, you get an imine, right? Same mechanism here. So now we are going to go from the hydrazone into this alkane. And that mechanism is something that you haven't seen quite yet. Well, that's what we're here to take a look at. That's the newer part of this reaction. So this hydrazone right here is formed after the first step. So now we want to go to the second step by adding some base and heat to get the hydrazone into the alkane. So what I'm going to do here is I'm going to take the one of these hydrazone hydrogens right here, and I'm going to extend it out like so. And the reason why we need to do that is because we're going to invoke the base right here from the sodium hydroxide and do a proton transfer. And so in this proton transfer, we're going to just have that guy come in and go like that. And then we're going to have a negatively charged nitrogen species. Okay. Now usually a hydroxide is not a strong enough base to rip off of a hydrogen off of a nitrogen atom. That usually does not happen. So this is a unique situation because what has happened here is that the reason why this can happen is because we have resonance stabilization. Okay. So if we take a look at our resonance structure, we could look at something that looks like this. We could bring in or bring down that negative charge and go like this. And remember, there's already a lone pair there, okay, like so. And then we can take these pi bonds right here and go like that. And when we do that, we have a structure that looks like this. So that's going to be neutral, and then that's going to be the carbon now has a lone pair, so that's going to be negatively charged like that. And so the reason why this sodium hydroxide can rip off this proton is because when you look at the conjugate base right here, it's resonance stabilized. Not only is this stabilized by resonance, but it's also stabilized by reduction. So this negative charge on that nitrogen is going to feel an inductive pull towards this nitrogen. So we have two ideas or principles that help us to understand why this is so stable. And because that is so stable, it then allows the hydroxide to take off that proton, when normally it wouldn't. But in this situation, it works. So now we have these two different structures here. So what's our end game when we look at our product? We need to get two hydrogens on that carbon, and we need to get rid of the nitrogen species altogether. So that's kind of what we're thinking about when we're looking at this. And so what did we just generate after I abstracted a proton? We generated some water. I'm going to expand that out like so. So now we see that we have a negative charge on that carbon there. So we can say, okay, we're going to take that lone pair there and grab that acidic proton on that water molecule. And so that's going to give us, let's see here, getting my correct colors here. So we have a nitrogen, H like that. Wait, I did not draw that correctly. So there has to be a double bond there. There we go. That looks better because I brought that lone pair down. Perfect. Okay, and what did we do? We added one hydrogen right there, and then we regenerated our base like that. And so what's the name of that step right there? That's just another proton transfer. Okay. Okay, so what can we do next here? Well, we have a base. We just added that hydrogen. What can we do next here? Well, what if I expanded out this hydrogen here, like so? Okay, now this is quite interesting here, because what we can invoke now is a E2 mechanism. Okay. Now, what's going to happen in an E2 mechanism? We're going to take that lone pair on that base, and it's going to come and grab that proton like so. The electrons between the nitrogen and the hydrogen are going to become and be added between the two nitrogen atoms. When that happens, this is going to break the octet rule. So we have to take the two electrons between the nitrogen and the carbon and break those and put them on the carbon. And we get this, our hydrogen. We just added, no, we didn't add another hydrogen. We now have a lone pair, so that's going to make that carbon negatively charged. And what left? Just like that. And what's another way of representing that molecule there? That's just N2. That's nitrogen gas. Now, when I take a look at the leaving group, so when we look at this part right here, what is the leaving group? Hopefully you can see that this right here is the leaving group. And are carbons good leaving groups? Well, when I take a look at what this molecule is and what it turned into, this guy is very unstable in comparison to this guy. So this carbanion right here is very unstable. It didn't want to leave. But then it begs the question then, why did it leave? And it comes down to this part right here. The nitrogen gas that's formed is the driving force for this process. Because when you generate a gas in a solution, what happens to the gas? It's going to bubble away. And when that bubbles away, Le Chatelier's principle kicks in. It's like, whoa, we're losing product, so we need to keep making product. And so it drives the reaction to completion, or it drives it to this part of the reaction. So yes, this is a bad leaving group, or this right here is a bad leaving group because the conjugate base right here is very unstable, but Le Chatelier's principle kicks in because we are losing product. And so now we have an anion right there. And what else was generated? This hydroxide turned into water, right? So now we can invoke, yet again, another proton transfer. And then that proton transfer will occur like this. Take that lone pair, boom, boom, and we will regenerate our hydroxide. And we would generate our alkane. Like that. Isn't that pretty slick? Pretty cool stuff. So that's the mechanism for converting a ketone or an aldehyde into an alkane using the Wolff-Kishner reduction. And recall from the beginning of the video, Wolff-Kishner reductions can be done under slightly acidic conditions. In step 1 and in step 2, you add the base and the heat. Or you could totally skip this step, right, the acidic version, and just go completely using base. And that mechanism is going to be slightly different, but you will get to the same answer. Now, under basic conditions here, the mechanism is going to be slightly different in the first part. Once you convert this guy into the hydrazone, then from that point to the alkane is exactly the same. The mechanism is exactly the same that I just previously showed you. So the difference is going from the ketone or aldehyde to the hydrazone under basic conditions instead of acidic. So let's go through a mechanism that makes sense and how it can work. Okay. So under basic conditions, we have a lot of base, a lot of water, and we have our hydrazine right here. So the first step would be that we would take some of our base right here, and we would do a proton transfer. We'd take that and generate the negatively charged species. Okay, so we would have NH like so. That would be negatively charged. So that's just another proton transfer. And now we can use this negatively charged species right here to attack the carbonyl. So we could come in and go like this. And what is that step right there? That would be our nucleophilic addition step. So that would give us a negatively charged species like that. We have a hydrogen there. So that's our nucleophilic addition step. Let's see here. Okay. Now, what else do we have in this reaction cocktail? We have water. So water can behave as an acid, right? So we could do a proton transfer. Now that was horrible. You don't go through bonds like that. So let's fix that. I was going a little fast and got a little sloppy there. We could go that way, go around and grab the proton. But don't go through bonds like that. And so that is another proton transfer step. So we're going to protonate this guy. H2. And then we regenerated some more hydroxide when we deprotonated the water. Okay. Now, what we can do next is we could invoke some kind of E2 mechanism here in which we can take the base, and then that can come and grab that proton, and then the two electrons between the hydrogen and the nitrogen can come and collapse down, kicking off the OH. And that's going to give us our hydrazone. And then what fell off? Hydroxide. Now, you might be freaking out a little bit because you're like, hey, OH, that's not a good leaving group. And that's true in most situations. But in this particular situation, we are increasing the amount of heat by a significant amount. And in some reactions, the heat could be around 200 degrees Celsius, which is a lot of energy. And so that extra heat can be the driving force to make this OH pop off. Okay? And another reason why it's possibly okay is because we are under strongly basic conditions. So now that's a proposed mechanism on how we would get the hydrazone. And now you would just take the mechanism that I showed you for acidic conditions in the part 2 and just continue on the same way. So now we have a hydrazone. How do you generate that hydrazone into the alkane? Just follow the same mechanism that's in this video. Okay, so I hope that is helpful. And that is the Wolff-Kishner reduction.